welcome to day 2 of the lecture series. I've been asked to make one announcement. So there's a lunch today for women in mathematics. So there will be pizza out there. Women are supposed to stay here, and the guys have to clear out in the Dixon Street now. So don't eat the women's pizza. Okay? So once again, we have Rafe, lecture 3. This morning is Wright-Fisher-Kimura Diffusions.
Well, good morning, everybody. So, as you can see, a stratified space. Actually, when you Google stratified space, you can find geology. For some reason, I got a lot of pictures of Whitney Houston, too, and I realized it took me about 5 minutes to figure out what was happening. Okay, so today I'm talking about something that's in the same ballpark as we were doing before, namely it's, as I promised you, sort of a case study of a certain type of a certain class of geometric equations that can be studied by the same sort of ideas which I was introducing yesterday. It fits into the same picture. It's not a problem that comes out of geometric analysis, though, as much of the rest of what I was talking about does, but rather a problem that came out of population genetics. And since it's joint work with Joe, that's easier. And identify this problem as something that fell within our capabilities, and it's turned out to be something also closely related to a problem in mathematical finance. And so this is just to show you that these types of equations arise many different places. So this is just a very brief description of where in the biology this comes from. So this is population genetics. And there's an old model called the Wright-Fisher model, which deals with a fixed population size of some genomes, and there's a large samples for each site. You have an alphabet that can occur, several different things that can occur at each spot, and you have sort of a replication, and the basic hypotheses of the Wright-Fisher model is you have a fixed population size, there's mutation and selection, and you try to track what certain traits evolve under this. Now, it's a fixed population size. It can be modeled by a matrix, so it's a Markov process. And as usual with these sorts of things, it's discrete models are both easier and harder to study, and they have, the discreteness can be either a benefit or a detriment. And people often look at the large population size limit. So here is the actual equation that you get by taking an infinite population size. So you're scaling, and I'm not going to talk about the details of this scaling process, just to present this to you as an equation that comes from the limit of the Markov process. If you take the population size to infinity, so what one has here is a heat equation. So for those excellent pointer again. So one has a parabolic equation. So we're interested in this type of process, diffusion process, and this operator element can do that. So I'm giving you the one-dimensional case right now. So this corresponds to the one wheel, and there's a multi-dimensional version which I'll write out in just a moment. This is sort of the simplest model problem. So you have a second-order part, x times 1 minus x dx squared. So you're on the interval. You can write this down explicitly. You're on the interval from 0 to 1. So if x is strictly between 0 and 1, this is a nice little developer. However, it degenerates, and in kind of a funny way, so rather a different way than I talked about last time, where I talked about operators that vanish on x squared times d by dx squared. Okay? So I didn't write down too many formulas in my lectures yesterday, but the types of degeneracies that come out of these geometric problems seem to have a different type of rate. And then you have the first order part. I know it's important in this biological application. There are two features of this first order part. One is that, so I have this term, so this is the simplest model where these are just linear and quadratic. The B0 and B1 are assumed to be greater than or equal to 0, and what that means is that this is a vector field that points inwards. Well, if B0 and B1 are equal to 0, then it vanishes at boundary, but if they're positive, then this is an inward pointing vector field. Okay, so that actually has biological meaning. And in fact, in the applications, typically B0 and B1 are strictly between 0 and 1. Or if it's greater than 0, it's 1. So these model the mutation and selection rates. And so you can look at this as a rather simple model problem to study. And there were various works going back to the work of Feller in the 1950s trying to understand this. Now, because it's coefficients or polynomials, there's a lot of sort of special tricks you can do. And there's some classic paper by in the 60s where he looked at the action of this operator on a space of polynomials. And if you think about it, this actually has kind of a special feature. If you apply this to a polynomial of degree k, well, the second order part preserves the degree, and the first order part also, let's see, maybe he didn't have this s part there, if I remember correctly. But the point is, if you set up, if you look at a particular model, then the first order part also preserves polynomials of degree k. So if you think about this on the vector space called polynomials of degree k, it acts like an upper triangular and lower triangular matrix. And you can actually say a lot about it and then try to look at the limit of that, and then use the density of matrices, polynomials, in this case, called continuous functions, and you got some mileage out of it. But of course, the information you can get by these sort of density tricks is very limited, and it wasn't really treating this honestly as an analytic problem. Okay, in any case, so this is the model problem, and it goes back a long time to the, I think, the Wright-Fisher papers from the early 50s or 40s. And as I pointed out, the really important feature here is that its first order term is inward pointing. Okay, so I've used this language about the generator, and the point is that for many applications and in mathematics too, you want to use this language of semigroups. So you want to think of U's being given by E to the T, L, so the WF stands for Wright-Fisher, makes this particular operator apply to F. As I say, this goes back a long time. The work that we were also very inspired by was a Japanese school in this Shimura and Kimura in the 70s. And they were able to study this using somewhat specialized techniques and gain a certain amount of ground, but very, I'd say, complete analytic study hasn't really been possible before. It hadn't really been attempted. But the types of questions, when you think about this, the next slide addresses this. So the types of questions that you're interested in is you want to choose some suitable function space. So this could be C0 in sort of the most basic sense, but maybe some more intricate space. For probabilistic applications, actually, C0 is exactly the right space you want to look at. And you want to let this semigroup act on this. And the questions you'd like to understand are, does it form a strong and continuous semigroup? And you like understanding of improvement of regularity properties and so on. So if you think about just the ordinary heat equation in Rn, for example, these types of properties are fairly standard and we cannot emphasize so much, but they're very important properties. And if you have a more complicated diffusion, there can be real work involved in verifying. So in particular, does the solution U, this T, L, W, F, converge to F in the norm as F goes to 0? There are many other modes of convergence, but this is sort of the nicest one, this form of convergence. And this actually is, I always like this kind of property here. So this is actually one way of actually defining Holder spaces. If you've ever learned this sort of harmonic analysis point of view, one way to actually, in Rn, of defining Holder spaces, you say, take a function on Rn, evolve it by the heat equation, and see how regular it is at time t positive. Well, it's smooth, so the question is you want to see how quickly the derivatives blow up as t goes to 0. Okay? And so in fact, there's a characterization that you can actually use as the definition of a Holder space, but then if you turn this around, or this may be the way you should in the first place, this is just a regularity property of the solution operator. This tells you how quickly it smooths things out. Okay? These types of estimates are quite they come up with. So these are types of things that one might like to verify. And again, I've stated this, say in a model case where this might be, for example, not L's of WF, where we, at the moment, don't maybe know this fully, at least before this lecture, but this is certainly the property that one has to be giving this. Okay, so I talked about the one-dimensional model before. Here's the general model that was written down, again, a long time ago. So this is in the biological parlance of multi-area studying, so I was looking at various traits, and you're looking how they diffuse through the temporal process and as mutation and selection have their way. So the A spaces work is a simplex. This is what naturally arises in scaling. And so one is interested in studying functions which are defined here. What the function represents is it's a probability density, right? So it's a density of a certain trait occurring. So this is sort of the thing that you're trying to track in time. How likely are certain traits to occur? And where this is taking place is on the simplex. And so this should look familiar from yesterday. This is stratified space. It's a polytope in Rn, but it's a very simple sort of object, and yet it's somewhat complicated in its own way too. So the geometry of this is a little bit complicated. And the operator we're looking at has this form, which is, doesn't look too bad, but it has the same feature. You have this xi, so at any one of these spaces where xi is equal to 0, I have the vanishing coefficient. And you have to work out the algebra a little bit to see what happens, but at the other face, where the sum of the x's is equal to 1, you have the same simple vanishing. Okay? So this model operator that was written down a long time ago has this geometric feature, and one thing you can codify is just try to understand what, for example, the symbol of that operator. You can ask what's the right generalization, what types of operators have this type of symbol. Okay, so let's just look at the n equals 2 case. If you write out what this operator is at n equals 2, you notice some interesting features about it. So again, near x1 equals 0, this term is vanishing simply, and this term is somehow lower order, as we'll see. This is kind of a negligible term. But if I look at the restriction of this operator to the space, now normally, if you're on a manifold boundary, you have a differential operator. It doesn't restrict the boundary face. Right? If you think about it, if I have a function defined on the boundary of a manifold, right? I have a differential operator defined in the interior, then it doesn't mean anything to invariantly say, what is that operator applied to that function just on the boundary, because the operator will involve normal derivatives. Okay? However, if the operator has this vanishing term in front of the normal, in terms of the normal derivative, then it actually makes sense to restrict the operator to that face. So this term's gone, that term's gone. What's left is exactly this term here, which is the Wright-Fisher operator in one dimension down. So another way of thinking about this is I have this nice two-dimensional operator, this operator which degenerates on the boundaries of the simplex, and every time I restrict it to a boundary face, I get the analogous operator on the corresponding simplicial boundary face. Okay, so that's a very nice feature of this.
You don't have any first-order terms in this higher.
So in this case, we will, but I just wrote down the second-order term. So in fact, the first-order terms are very important, and we're going to assume, as I'll write down in just a slide or two later, that we have a second-order term that looks roughly like this, plus a first-order term which is at least not outward pointing. So it's either tangent to each boundary face or inward pointing.
So basically, if you've eliminated one allele, you've got the same problem with one fewer alleles.
Yeah, that's exactly right. I mean, another way to think about it, if the vector field is not pointing inwards, then once some trait becomes extinct, it stays extinct, and then you sort of evolve in a world of things where that trait just doesn't appear. So, yes, that's good. Okay, so I want to talk about the two works. One was the one-dimensional case, where we're sort of getting our chops in this business, which we have seen. And then what turned into sort of a very large project trying to understand the multidimensional case. So what we sort of hoped would be not quite a weekend project, but something that we're much of years and hundreds of pages. So, and the techniques I'm going to describe for how we're treating it. So I described to you many different approaches to degenerate equations yesterday. At least indicated there are many different approaches. And there's no doubt that this probably could be approached by other methods. I think that our final analysis, what we realized was that no matter how you approach it, it's a hard problem. It's a technical problem. It takes a lot of work. So, the approach that we ended up taking is, in some sense, a more classically minded approach than I might have been tempted to otherwise. But I think that any single way you can do it would just take a long amount of development. It's a technical problem. Fortunately, it's one that people seem to be interested in the answer to. So, in any case, some of what was motivating us were questions from real-life biologists who were interested in, so the questions that you're actually interested in are what are the regularity properties at the boundaries of the simplex. So at some later time t, you'd like to understand what's the exact rate of decay as you move to the boundary. What are the fine regularity properties tend towards the boundary simplex. It actually has some interpretations. Okay, so we geometrize this in the sense that we don't just look at these special models on simplices, but in the spirit of all good abstraction, we just think of what is a reasonable general class of problems that we can treat by a general method, where we have to use more or less the same method even for the specific model case. Okay? So what we do is, instead of thinking about the simplex only, we look at any manifold of corners. Okay, so a manifold of corners is, I didn't sort of talk about this so specifically yesterday, but let me just say a few words. So a manifold of corners is the manifold. So you're used to thinking of a closed manifold as as something where at any point there's a coordinate chart which models, which is diffeomorphic to an open ball, let's say in Rn. So that's the standard definition of a manifold without boundary. A manifold with boundary, the standard definition is at any point you're diffeomorphic to an open ball in either Rn or Rn plus, right? So just the boundary, or just the half space or the full space. Okay, so if I have a point here, then it's modeled by half ball here. Okay. So similarly, a manifold with corners in codimension 2 is something that's modeled by. So if I have something here, it can be modeled by the positive quadrant in Rn. So namely, the set of x such that x1 and x2 are greater than or equal to 0, the other variables are free. Okay? And similarly, you can talk about the positive orthant in Rn, so k of the variables are non-negative and the other ones are free. And the manifold with corners is something that's modeled on that. Okay? So notice that this disallows various things that might tend, well, that certainly occur for stratified spaces. So for example, suppose I have, the other side of a corner. Something like this. Well, if you think about that, that's not actually a manifold of corners. Okay, it's a stratified space. So there are various things that are disallowed. Another thing, if you're interested in studying polytopes, which very reasonably should be, there are polytopes that you might see in R3 that are not manifolds of corners. So let's suppose you have a 4-valent vertex, right? So you can have, let's say, a triangular prism. So I drew a terrible picture here, but this is the top of a pyramid where the base is a quadrilateral. Okay? So that's not a manifold of corners simply because, a point here, that vertex there is not modeled locally by orthant in R3. Okay, so there are real restrictions in restricting this category. There is this sense of blowing up a corner. In fact, given something like this, you can always turn it into a manifold of corners by introducing polar coordinates at that corner. In this case, you get something which is somehow resolves this vertex into driving the vertices. So I don't want to talk about that. This is a reasonable restriction. So we talked about manifolds of corners and operators which are defined on these manifolds of corners. So these are the elliptic operators that are going to be the generators of diffusion. And they have the following characteristic properties. So they're elliptic in the interior, and you have this characteristic property that at each boundary face, the second derivative, the d by dx squared term, if x is the normal variable to that face, has an x in front of it. Okay? What about the other terms? Well, they're mixed terms, like the dx dy terms, and I assume that these are low order, that these instances vanish in space. I'll talk about that. I'll write out a formula in the next slide or two. And then this other property, which is that terms which are tangential to the face don't vanish. So you have this property that the second order part really restricts to give you an operator of the same type on each boundary face. Okay? Okay, so we then add to the second order part a first order term, which is a vector field, and we make the following assumption on it, which is certainly a technical convenience, and it may be sort of a reasonable one too. So we assume that at every boundary face, the vector field either is everywhere transverse or it's everywhere tangential. Okay, so you don't have any situations which you can imagine analytically where the vector field, somehow is tangent along some very complicated subset of a face and then becomes transverse on some open set of the complement of the face. So we assume that each face has a curve, has one or the other type of only, and as dictated by the applications, we're looking at operators where there's no true zero. Okay? So if I were to just write down the second order operator with these properties in one dimension on the interval from 0 to 1, then what I'm demanding is that this coefficient a of x vanishes simply, so order 1 at x equals 0 and x equals 1, and this b has these sign conditions at the endpoints. That's all I'm asking. Okay. So if I now look at the case where I have a manifold of boundaries, before I write down the general formula, which is rather complicated, so I wrote down the one-dimensional case on the interval. Okay. Now I want to write down the case where I have a manifold of boundaries. So there's no corners, so there's only one variable x going to the boundary. And what I'm demanding is the following. So the boundary is where x is equal to 0. I use tangential coordinates along the boundary. And here's what the operator would look like. So a priori, it's some second order operator. I'm demanding that this term here vanishes to order 1, and that this term also vanishes, but that this restricts to an elliptic operator on the boundary, and v is either everywhere tangential or everywhere transversal. So, so there's the restriction of the second order part. So I didn't explicitly pull out the second. I didn't pull out the vanishing term from here. I'm just saying that A00 has the term x times something else. Okay. And so finally, here's the general case. You can see why I didn't necessarily write it down right away. It's a little bit difficult to parse, but it's not so complicated. So manifold of corners, I can choose coordinates near any point at a corner, where I have a number of variables, x1 through xk, which are greater than or equal to 0, and the remaining variables are just in an open set in R L. I have it, so these are just local coordinates. 0 to epsilon minus epsilon to epsilon. The boundary hypersurfaces which are meeting at that corner are where any one xj is equal to 0. Okay, and you have corners of various codimensions where any collection of the x's vanish. Okay, so in particular, the maximal codimension, right, at least locally at this point, is where all of the x's vanish. Okay? And so here's the form of the operator that we're looking at. So this is a reasonable generalization that encompasses all of these various Wright-Fisher-Kimura type models. Is I assume that the second order part has, well, I'm singling out the diagonal bits and the rest. So the diagonal bits have this extra order vanishing, xi, times these aii's. The aii's are strictly positive, right, so that they're not vanishing. And I include the first order terms here right away. So this is the part that's differentiating normal to that boundary. Okay? Here I have the mixed corner terms, the xi, xj second derivatives, and I assume that I have xi times xj. Okay? Here I have the corner slash the xy second derivatives. They have an x factor of xi. These guys are non-degenerate. Those are this is the part of the operator that restricts to an elliptic operator on the corner itself. The corner is a codimension case of manifold. And here's some bit which is tangential. Okay? So the c's and the aij's are positive definite, and so on. And we have this non-negativity condition on these coefficients here. Okay, so it's a bit of a complicated formula, but again, this is meant to be a relatively straightforward generalization of the one-dimensional case and of the higher dimensional case that was written down that just had polynomial coefficients. Now, something which I'm not going to mention in this lecture is that from various points of view, both analytically and maybe in terms of applications, you can ask, why do I have factors xi times xj? Why couldn't they be something else? So one thing is I'm assuming that all of these coefficients, the aij's and so on, are all smooth functions. You can obviously lower the regularity requirements on these. But what if I lower the order of vanishing? It turns out that the natural order of vanishing, which is not apparent if you just look at this form of this operator, the natural order of vanishing that you can hope to control is where this is the square root of xi times square root of xj. So I just have square root vanishing instead of full powers. If that's the case, I need to assume that the aij's are not too big. But it turns out that square root of xi, square root of xj times aij is somehow the term that, in the most natural sense of the scaling of the problem, which I will talk a little bit about later, that's the right one. Okay, now, excuse me, one thing I want to do, so forgive me, I'm going to flash back to something I did in the, let's just go here and go to something I talked about in the very first lecture. Yes, so in fact, we just a couple of slides which I just talked talked about very briefly in the first lecture, and because I was pressed for time, I'd like to just review these a little bit now. So, find a second-order operator. Remember I talked about various types of degenerate operators, and here was one which I'd said, if you just looked at that and said, well, I would like to analyze this by classical methods, you'd be pretty much out of luck because it looks badly degenerate. But what saves you is the fact that it's the Laplacian associated to the hyperbolic metric. And if you use the geometry of the hyperbolic metric, you can actually go a long ways. And in fact, you then sort of say, I want an operator that has the same type of degeneracy as this. Now notice this has x squared times d by dx squared and x squared d by dy squared. Right? And there's an x in front of d by dx. The right way to generalize that is to say that every time you have an x or y derivative, it's accompanied by a factor of x in front. Okay, so this is the type of degeneracy that we're allowing. The zero-Fourier term doesn't have any special properties. Okay, and again, the AIJs, the ellipticity condition is that once I've factored out these xdw derivatives, what's left over, the coefficient that's left over, is required to be positive, definite, up to the boundary. So that's not ellipticity in the usual sense, that's ellipticity in this degenerate sense. And it turns out that there's a great framework that's somehow inspired by hyperbolic geometry that allows one to study this. Now, something which again, as I say, I flash by these very quickly, but suppose that with manifold boundaries, now we're actually in the category of what we're talking about now in this lecture. So suppose I have a vector field which vanishes at the boundary. That means that I can just factor out an x from each. So if I have smooth functions that vanish at x equals 0, then I can write it as x times a x y and x times b x y. Okay? So the right way of thinking about this operator before is that it was combinations of vector fields which vanished at the boundary. Now, in lecture 3, which we're talking about this type of operator as being sort of a prototype of a manifold boundary, y is boundary coordinates, x is sort of normal coordinates. This is exactly the type of thing we're looking at. And the point I want to make here is that this is really just one of these uniformly degenerate operators in disguise, at least when you're on a manifold boundary. Okay? So this is something that degenerate operators, as I said in lecture 1, can be disguised by coordinate changes, and you have a much richer class of coordinate changes on the manifold boundary than you do on a orbit. So what are the coordinate changes I want to allow? So the first thing I want to do is multiply by an overall factor of x. So, that looks a little bit suspect, and especially if I'm looking at the heat equation, d by dt minus L and d by dt minus XL are very different sort of operators. Right? So this looks a little bit suspect, but it turns out that that's not such a horrible, radical thing to do. So I multiply this operator by x, and then I do the following change, which is a non-smooth change variable. I let c be the square root of x. When I do that, the short calculation gives me exactly one of these uniformly degenerate operators. So in other words, this operator, which doesn't look anything like a uniformly degenerate operator, it's degenerate in a very different sort of way, actually is one of these things that I described geometrically in disguise. Okay, so that's the point that it's probably appropriate to make at this point. So let me go back to 3, where was I? Okay, so we want to construct key kernels for this general class of operators I described before. And so what I'm going to be describing for you now is an analytic construction of key kernel. Now, for those of you who are experts in this business, there are many different ways to construct parametrices for heat kernels. I'm going to describe one which, from some points of view, is rather crude, but given the complexity of the problem, because of all these corners and so on, it turns out to be a very efficient way and gives you almost as much, but not quite as much information as some of that I have. So the thing to think about, focus on in all of these types of problems is what are the models? What are sort of the quote-unquote constant coefficient models? And in one dimension, this is the model operator, right? I choose a constant b which is greater than or equal to 0. And in higher dimensions, I take sums of these things plus the tangential Laplacian. So these are the model operators I'm interested in analyzing. And so the technique is sort of the standard one that you're familiar with, which is understand the model operator completely, which we rather remarkably can do, and then perturb off of that to get a solution to the general operator. So you somehow have to string these things together. And unfortunately, that takes a bit of work, but the general conceptual string is not so difficult. So here's a rather remarkable explicit formula. So the one-dimensional problem, so I pose this, and this L is the one I wrote down for x d by dx plus b times d by dx. There is an explicit solution operator for any f here. And notice I'm on the half line, so I'm not restricting to just defining an interval. There's an explicit solution operator. So it's an integral operator, just like I expect b equal to b. And here's this function, k sub b, which is this garden variety function. This formula, we had sort of a Fourier analytic version of this formula before, and Charlie Pfefferman was thinking remarkably about similar types of problems. Actually, it's an odd explicit formula. It's sort of a great stroke of luck for us. So here it is, and this I sub b, this is a Bessel function of order. This is the Bessel function on the imaginary axis, and this is the exponentially increasing one. You might worry that this is exponentially increasing, so that doesn't have Gaussian type behavior. But if you think about this, here I have something that's vanishing like e to the minus x, and this is only growing like e to the plus square root of x. So these things just cancel out if I look at the asymptotic of i's, I get typical Gaussian behavior. So this is a pretty interesting function, and it has those things wrong. Notice that this is very non-symmetric, but that's no shock. The operator we're looking at is very non-self-adjoint. We're not using any sort of Hilbert space theory or self-adjointness. Okay, so there's our very explicit operator. And the higher dimensional analog of this, well, E-kernels are multiplicative, so if I take the model problem and just adding a bunch of these plus a Euclidean operator, I just multiply the corresponding E-kernels. Okay, so that's it. There's a very explicit formula. And the main analytic problem, as I've said, is how can we look at this very explicit solution? So we have sort of two jobs. One is to say, what are the fine mapping properties of this very explicit E-kernel, right? How does this happen, C0 or whatever other function space we might want to write that on? And then how can we do a perturbation analysis to go from model problems to variable coefficient problems? And it's that second step. I mean, I really want to emphasize from some point of view that, understanding the model problem is the hard work that you have to do in any approach. So no matter how you're approaching a degenerative problem, there's some model problem, and then there's where your hard work lies. You have to figure out what your model problem is, and then you have to learn everything about it. Sometimes it's easy. There's a Fourier transform or this and that, it reduces to an ODE, and it's not such hard work. But there's always some kernel of really hard work that you have to do. And then after that, there's going to be some sort of glorified perturbation analysis, which may be packaged in one way or the other, and which is a very real part of the problem too. But somehow that's something that you can formalize this independently. If you're faced with a particular operator, you have to analyze a particular model problem. Okay, so here's the parametrics construction so first of all, in local coordinates, so suppose I just choose coordinates near a corner point, so x, y, and t again, and I'm interested in the variable coefficient operator L, so this big two-line monstrosity I wrote several pages back, right? And well, what I'm going to do is just take functions which are, let's say, compactly supported in a small coordinate neighborhood, apply the model E-kernel to it, and see what happens when I take that model solution. Of course, it's not an exact solution to the real thing. What I get is that if I take dt of u minus the variable coefficient version of u, I don't exactly get 0, meaning that I get u. U at time 0 is f. I mean, this is, of course, this has the property that it's equal to the delta function at time t equals 0. So that part is okay, but it doesn't exactly solve the equation. So there's some error term here, and you have to analyze it. And, this is sort of the usual yoga in any sort of analytic construction like this, is that you have an error term and you want to show that it's morally small. Now, moral has two meanings. One is, ideally it would be a compact operator, which is also small in norm. This is small in every good sense, well, small in every sense of the word 0, but, failing that, it could either be a compact operator or it could be a small norm operator. Notice that both of those senses have meaning only relative to a given function space. So I have to think, when I'm acting on a given function space, when is this thing small? Okay? And here's sort of one of the unpleasant facts here. Remember that we wanted to let this thing act on C0, so our part. Well, let me give you a bit of background for this. So there's a theory that goes back to Kolmogorov where for studying this Markov process, you actually want to look at the adjoint operator acting on measures. Right? And that's called the Kolmogorov forward equation. The thing that we're looking at is, for your reasons, called the Kolmogorov backwards equation. Okay? That's the way it goes. and it acts on, well, the pre-dual measures, namely continuous functions. Okay, so that's why, because of the probability, there are measures there for the forward equation, there's C0 for the back equation. So ideally, I'd be letting things act on C0. And here's the very unpleasant surprise, which is that if I take the operator that we looked at, that, and I apply this model heat kernel to F, and I compute dt minus L of u, I get an error term, and unfortunately, this error term we cannot prove on C0 is small, right? It's not compact or small. So that's partly a deficiency of our methods, but it's partly just sort of, well, I'll try to explain the issues a little bit later on. So somehow or another, there's a possible, well, it's just not a small term. So part of the problems that one has to do is one has to find function spaces that are well adapted to the problem so that this E actually is small in one of these senses.
Right?
Yeah.
Does the dual problem have the same operator of the same character?
So no, the dual problem, so let me go back to, well, let's just even look at, there's the problem. Think about what the dual would look like. So the second order part would be fine. One thing that the dual would definitely have is zero order terms. Because when you integrate that part 2, you get 0 over 0. There's another huge difference. So one thing I've stressed here is sort of what is the expected behavior in technical language? What are the initial roots as x goes to 0? Okay? Now there's something quite remarkable that happens about any operator of this type, which I'm going to say rather explicitly a few slides on. For this backwards operator, the initial roots are 0 and then something else that you discard. Okay? For the forwards operator, the initial roots are that thing that you discarded becomes the guy that you have to now pay attention to. And here's the sort of bad thing. There's no reasonable way to say geometrically that this B is a constant. So in other words, here's sort of the problem where there's no really nice way to say that you have constant initial roots. One of the initial roots is constant, right? Unfortunately, for the problem we're studying, that's the one that you focus on, right? But the other initial root is variable. And you just, So the other equation, the adjoint equation, is not because it necessarily has variable initial roots. Okay? So that's an aside, but I'll come a bit back to that later on. I don't want to get into that issue strongly, but that's the fact. Okay, so here are the difficulties. So the first is that the operator L, if I look at how it differs from the constant coefficient model, there's second order perturbation terms. So if you forgive me for going back one more time, here's this operator, but here's the model operator part. Here are some of the terms that deviate. First of all, I have to look at what happens when I look at the difference between AII xy minus AII 0y. That's not too bad because it has an extra order of vanishing. But then I have these second order derivatives, okay, and so on. So there's the L minus the model L is a second order operator, sort of inextricably, at least in higher dimensions. Okay, so that's one problem, is that E is going to involve terms that involve second derivatives. Maybe some factors of x or maybe not apply to the model E kernel. And the point is that these typically are just bounded, ideally, but not necessarily small. And in fact, here's the issue where C0 comes in, is that the heat kernel in higher dimensions is, it doesn't map C0 to C2 in a natural way. So if I take two derivatives of the heat kernel, it doesn't deliver C0 in a very natural way. It's not strong enough to C0. So this is a very problematic type of error term when you're acting in C0. Okay, and then the other point is exactly the one I've raised here, is that the first order term has these coefficients B, and they vary. They're sort of a variable term. Now, it turns out that for the problem we're studying, that we can get around that. Locally, the variation is not too large because they're smooth functions. So we work in small neighborhoods where B is almost constant, and then, for that. But, okay, so it's possible to do all of this, and one trick to think about, so this is again sort of a standard transition in the business, but I just wanted to remind you of it if you haven't seen this sort of thing before, is that instead of just looking at this homogeneous problem to do this whole analytic theory, it's more convenient to think of the inhomogeneous problem, where I look at dt minus L of u is equal to g, where u vanishes at time 0, versus the problem where dt minus L of u is 0 and u is some given function at time 0. Okay? These problems are equivalent. There's this famous old Duhamel formula, which tells you that if you know what the heat kernel is, then you know how to solve this inhomogeneous problem. Okay? point of doing that is that if I look at the curved operator, L, acting on this model heat kernel, dt minus L acting on functions of tx and y is the identity operator plus E. But the point is, this is, identity is invertible, and E is an error term, and the goal is to show that E is small so that this Neumann series makes sense. So I have dt minus L of K is equals to identity plus E, and if E is small enough, then identity plus E inverse exists. There's an explicit formula for it, which makes sense if E is small enough. And there is the proof of K times identity plus E inverse. Okay, so we can make sense of this, but as I pointed out before, we have to worry about what function spaces we're attacking. Now, when we got to this multidimensional setting, as I mentioned several at the beginning, written earlier a paper on the one-dimensional version of this. The one-dimensional version, almost all of these problems are concealed for an interesting reason. So this is actually something that, as I told you, Feller had been studying in 1953 and 55. There are a couple of seminal papers on this business. And he noticed that if I have any coefficient a of x, which vanishes simply at x equals 0, then there's a change of variables which straightens out that coefficient to x. I mean, this is just a simple calculation that no matter what the leading coefficient is, if it vanishes to order 1, if I change x to some c, which is just a diffeomorphism, I can make the second order part just x d by dx squared. And all sort of variable coefficientness happens in the first order term. So what does that mean? It means that if I look at the error term, it's just first order derivatives applied to the model problem. And those are always controllable even times C0. Okay, so I never have the problem that I have a second order derivative applied to the heat kernel, which is up down. Okay, so in fact, in the first order problem, you can do quite a bit more. Now, I'm not going to say too much about the techniques and how we do it. I mean, we have this parametric construction, which is given by taking the model heat kernels and binding them together, and just using a partition of unity to take an arbitrary function, I break it up into things with small support, centered where the coefficients are not varying too much. I apply the model heat kernels, I relocalize with the partition of unity, and then I show that the corresponding error term, is not too big. Now, as I said, one of the big features here, and this is again very typical of the general problem, is that you have to work hard to find good function spaces to make this work. And it turns out the adapted function spaces here have this sort of odd scaling property. It's not too shocking if you think about the form of the operator, but it's not obvious from just staring at it without anything. So I forgot an equal sign here. But so these are what we call Wright-Fisher-Holder spacers, the WF Holder spaces. And in one dimension, if I look at just the simplest versions, I'm not going to do the full scale of spaces, and there's various modifications of these, but the alpha semi-norm is where I take the difference quotient, but instead of taking x minus x prime to the alpha power, that's in the definition of ordinary Holder spaces, it's square root of x minus square root of x prime. And actually, this is related to, suppose I go back to the one-dimensional problem. So x d by dx squared. D by dx. So here's something which is a little bit surprising. Suppose I set c is equal to the square root of x. So this is the same change of variables I did way back when. If b is equal to 1/2, I believe that's the right number. There's some choice, I'm pretty sure b is equal to 1/2. This thing is just d by dc squared. Okay? So in other words, this is a completely non-degenerate operator in a singular coordinate system, at least for this particular value of b. Okay? But it's exactly this power here, the square root of x, which indicates that in some sense that's the natural variable to be using, even when b is not equal to 1/2, that's the natural variable to be using here down here. Okay, so that's in fact exactly the variable we used. Now, here's a little bit about the boundary behavior. So something which should be shocking to any self-respecting analyst, because I've been talking about a PDE on the boundary, and I never talk about boundary conditions at that boundary. Right? Now, again, this is kind of a feature that we see in many degenerate problems, that the boundary condition can be concealed in some sort of growth condition. Right? Now, the growth condition we're using here is not a standard one, and I want to describe it in a little bit of detail at least. So the issue is the following. If I look at just a one-dimensional problem, this is like what I call the separation of variable solutions on cones. I can say, what are the solutions that just look like powers of x? Okay, that's a reasonable thing, a reasonable ansatz to try to find a solution of the stationary problem, else be equal to 0. And you can find that there are two solutions here. One is x to the 0, which is the constant function, which is always using a constant term as an operator. And the other is x to a funny power, x to the 1 minus b. Remember, b was greater than or equal to 0. When b is equal to 0, there's actually a, you have to worry about logarithms, but let's think about b being strictly positive. This is a power strictly less than 1. And in particular, when b is equal to 1, there's going to be definitely a log term because I've repeated the initial root. And when b is greater than 1, then this is actually negative. Okay? So I could say, if b were greater than 1, I could say, I'm just interested in bounded solutions. And that would say that I knock out any possibility of x to the 1 minus b. But if b is somewhere between 0 and 1, then, you know, this is actually better behaved than this in some sense, right? And it's bounded and vanishing in some way. So here's what goes into it. If I take any smooth function on the right-hand side, if I look at else b is equal to g. So here's a general regularity term, the very same type that I described on cones yesterday. So I take this degenerate operator, applied to u is equal to g, any solution, not just, you know, ones that have an a priori condition on them, any solution whatsoever necessarily has this form. It looks like a smooth function plus another smooth function times x to the 1 minus b. So I'm assuming I'm in a case where b is, let's say, strictly between 0 and 1. There may be log terms when b is equal. Okay? So this is just, you know, a general form. Now what capital A and capital B are, well, they depend on g, of course. And there's some integral expression that may describe this. Okay? And the boundary condition, so what's true about these types of asymptotic expansions is that if I know what the leading coefficients are, if I know what A at 0 are and B at 0 are, then I can determine the whole Taylor series. How does that work? Well, suppose I just plug in the Taylor series for A and the Taylor series for B times x to the 1 minus b, and I substitute it into this equation. Right? Well, I get a recursive series of equations on the Taylor coefficients. The leading terms get killed precisely because the leading exponents are x to the 0 and x to the 1 minus b. And then all the higher terms cancel each other out, provided I choose the coefficients aj and bj appropriately. Namely, there's a unique way to choose the higher terms in the Taylor series so that you actually get a solution to this equation. Okay, it's a formal calculation. So there's two things going on here. One is sort of a real regularity theorem, which says any solution that looks like this looks like the sum of two terms, smooth and smooth times x to the 1 minus b. So that's a real regularity theorem. Okay? The minute you have that real regularity theorem, then what these terms are is determined by a formal calculation. You choose any initial terms for these two smooth functions, then everything else gets handed to you by algebra. Okay? It doesn't tell you what A and B are doing in the interior, but at least it tells you what they're doing in the infinite order of the bound. Okay, and so what we're looking for are solutions where B is 0. So there's no x to the 1 minus b term. And that's enough by what I've just been saying to say that the leading coefficient B of 0 is 1. Okay? So as I say, we're interested because the applications in the case where B is in the open interval from 0 to 1, for example. X to the 1 minus b is bounded and not differentiable. And the boundary condition we're imposing secretly is like a Neumann condition. So the condition is that x to the 1 minus b term in the expansion of solutions is not there. And that can be rephrased as, if I take the derivative, so dx of this is gives me x to the minus b, x to the plus b will give me the leading coefficient now, as x goes to 0. Okay, so this is a way of specifying this sort of, the dx of u itself would, in general, be singular. It would be blowing up as x goes to 0. But the coefficient b of 0 is singled out by this particular list. Okay, so this is a type of Neumann condition. Now, going back to this language of initial roots, I have these two initial roots, 0 and b. And for the model problem, they're constants, right? But for the real problem, 0 is 0. It's not varying, but b is varying. So the thing that we're knocking out is x to the b term, which we're knocking out by the regularity of the point. The requirement that the solutions be smooth, not like this x to the 1 minus b equation. The regularity requirement is actually allowing us to never worry about variable conditions. So that's kind of a miracle in fact, we're allowed to do that. So for those experts here, you know that variable condition roots are either a pleasure or an entire catastrophe. I tend to be the latter camp. So, but the question is, suppose I were forced to deal with things that had expansions like this. Well, dealing with this b of y in an exponent, you have to work very hard to make good sense of it. It's possible, but it's hard. Okay, so that's the boundary conditions. So here is getting back to the question that Robin addressed a few moments ago, so I'm just finishing up with the slide next. So the solution operator that we finally get at the end of the day has this remarkable property, which is forced by the boundary condition that we've been discussing, that k is smooth as x goes to 0. Remember, x could be this multidimensional corner variable, x1 through xk, but you're smoothing those variables as x goes to 0, and all of these sort of complicated asymptotics we're allowed never to conceal, but we're allowed to never have to deal with directly because they're in the incoming variables, which get, have the identity plus e inverse, and they're just junk that we can forget about. Just the stuff that's coming in. What we're worried about is the outgoing regularity. So it's a very fortunate thing in terms of technicalities. One might well want to understand the so-called forward equation, dt minus L transpose, in which case, and there are reasons from the applications to do so, and that would then require careful attention to these. Okay, so I think that's all I wanted to say about this equation. Just a few more words. I mean, we chose what is, in some sense, very similar to the parametric construction you can do for the ordinary heat kernel, let's say, on closed manifolds where there's no boundary. You just take sort of local models and piece them together and then show that the error terms are small. And, the real innovations here were, first of all, finding the right function spaces so that those really were good approximations. So something that looks like it should be a good approximation isn't on the function space that you most likely to. So that was sort of, and then it just takes, as I say, no matter what approach you take, you have to study the model problem and understand its regularity properties carefully. And sort of the bulk of our work on this is exactly studying the regularity properties of a model operator. So perturbation analysis takes work, but the really hard work is understanding the regularity properties. Okay, so this was, let's say, a very non-geometric talk on some level. This afternoon and tomorrow morning will be intensely geometric, so I just wanted to give you a respite from that, if that's not Well, so in fact you can, and how shall I say, you became aware that that was the right thing to do only after we wrote an appendix in.
Well, it's okay in the hypersurface case.
That's right.
In the hypersurface where there are genuine corners, it would be extremely complicated. Right?
It
If
does
you tried to
require
get into microlocal, geometric microlocal machinery, you would be faced with all of these corners meeting and a product space, many more corners meeting. And
no, he's asking two different questions. He's asking a slightly different thing, which is, even with our approach, why didn't we allow the square roots originally? And there, it's just a matter of, the same but more so.
Yeah, you could.
You could, and we didn't, but we should have. And why didn't we do it with the geometric microlocal machinery, which is Charlie's response, is it would take a hell of a lot of work, because when you're dealing with the general manifold corners, you have to do you have two big blow-ups, it would be a mess. I mean, it's possible, but I'm not convinced. I used to be convinced it would be a much better way to do it.
Right. But also, if you don't multiply the operator through by x, then we have this term that's not degenerate. You have this none, which would become singular if you replace it with. You would have a 1 over c e by c term, which would be very nasty.
I mean, it may well be possible to do that. There are various coordinate traits and multiplying and so on, but it's not necessarily significant in the same way. Probably not. Yeah.
So can you use this kind of flow to go to infinite? To get some coordinates in order to solve some kind of elliptic problems.
Yeah. So I talked about the parabolic problem rather than the elliptic problem. So there's this nice transform that goes back and forth from the heat kernel to the result of the Green's function. If I just take the heat kernel and integrate it from 0 to infinity, I get the Green function of this operator. And if you take that times e minus t lambda and integrate that, then you get the resolvent. So in fact, you can get the resolvent from this, and we do that. And you can get at least very And of course, it could equally well be possible to look at the, let me tell you sort of one important point of using the heat kernel. This is actually a rather interesting and important feature. So we could have studied the elliptic problem purely and then taken the contour integral to get the heat kernel, if that's what we were interested in. But here's a really good reason to use heat kernels if you're looking at corners. Multiplicativity. If you have a sum of model operators acting on different spaces, how do you get from, let's just say, suppose you have L1 plus L2, they act in different spaces. You want to understand the resolvent of L1 plus L2. Well, this is something that Andras and I did several years ago. And, you know, it's complicated. I mean, you have the convolution of the resolvents of the two pieces gives you the resolvent of the sum of the operators. But that's an inherently complicated thing to understand. Whereas heat kernels just multiply. See, so if you're working in product spaces, heat kernels have a huge benefit.
You made a slightly flipped comment that I'd like to just ask
Please,
about relating the heat kernel for L and the heat kernel for X times L. So can you really could you really derive properties about the heat kernel for X times L?
Well, okay, let me say this to you in technical language, which is the following. So if you look at dt minus L and you multiply the whole equation by X, you have x dt minus XL. And if you're looking at the geometrical microlocal point of view, then they're just a different blow-up. So instead of blowing up the corner for all time, you're just blowing up the corner at time 0. So, you know, the point is, you can handle it perfectly well if you have an x dt, right? So forgive me for non-experts, but let me just answer the question. And let me just point it out on a cone, because this is exactly what happens on cones. Okay? Suppose that I have dt minus, dx squared plus 1 over x dx plus 1 over x squared d plus h, right? And I want to think of that as x squared dt minus a b operator. So minus, x dx squared minus a Gaussian h. Okay? What is the right blow-up picture? So again, forgive me for those of you who are not in the midst of this business. So, the heat kernel is supposed to be a function of xx tilde and t, and because of this extra factor of x squared, what you do is you blow up the corner t equals x tilde equals 0 parabolically with respect to this. This is your model face, and in terms of a rescale time variable, so if I let tau be t over x squared, x tilde squared, let's say, that's the time variable on this face. That's going from 0 to infinity, but sort of infinitesimally at t equals 0. So it was meant to be a flip comment because, from some point of view, it's an easy transformation.
So for the model, does that mean you can actually relate the model, the heat kernel for XL and the heat kernel for L? What does it mean?
No, I mean, it's saying that, there's the same package of ideas will allow you to do one.
And like, see if you can do the other. But,
yeah, I mean, how shall I say? When you're doing this, I mean, if I look at x squared dt minus x dx squared minus the Gaussian h, there is a blow-up that handles this type of degeneracy. In fact, you also have an x squared in front of the dt, right? It's a different blow-up than if you didn't have the x squared. But, so it's not, the model problems are different, and,
I see.
So
the same techniques.
The same type of techniques. And I guess, actually, forgive me, the model problem is probably exactly the same. So in terms of this rescaled time variable, I have d tau minus, s ds squared minus the Gaussian h. So if I blow up the other way, which is I blow up the entire corner for all time, I have a model problem that lives here in terms of the unrescaled time variable. That's if I had dt minus x squared times the other operator, right? So what I'm saying is that there's some sense an equivalence between the two model problems and those two faces, but those two faces are playing extremely different roles in business. But it's the same model. Part of that's allowed by t is kind of a canonical variable. T is, it's a product separation.